Okay, today I'm going to start to talk about some of the laws that we will use throughout the course. Probably we'll use it up to the very end of the course. And there are three laws that we are going to talk about them. There are two of them. They're called the Kirchhoff Laws, and the third one is the Ohm Law. These three laws are very basic tools that we are going to use later on in circuit analysis. I will work through that to see how many of them I can cover. But I start with the Kirchhoff Law. So these three laws, I will say, these are extremely important. We will use them over and over and over again. And so just make sure that you follow them truly. So the very first one, the first one that we want to talk about is the Kirchhoff current law. Or if you go, usually it is shows with KCL. They call it KCL. The Kirchhoff's current law is the or KCL. So it's the very first law we will cover, and we use it. Remember when it says that we can use the analogy between the water and the electricity when we want to work with that. Now let's start. Before I explain that, I assume I have pipes, three pipes. That I have one pipe coming here, and then I have the two pipes leaving from that. So assume I have a point A, B, C, and D. So I have pipes going through. So if I look at that, you all know that, well, if there's a water coming through pipe A, so if I have the water goes through pipe A, and then it will split between these two. So if whatever water I have, and then it comes and split in these two. I know that whatever water comes to the point B, if I only look at the point B, where I pipe split into two, whatever power, whatever amount of water comes to point B, that amount of water is gonna be lives in pipe BC and BD. So for example, if I says that 1 gallon of water comes to point B, 1 gallon of water should leave that point B. So maybe it's going to be half and half, maybe it's going to be 0.3 and 0.7, maybe it's going to be 0.6 and 0.4, but if 1 gallon per second coming in, 1 gallon per second in total should leave point B. So whatever, if I look at that junction here, whatever water enter that junction, that amount of water should leave that junction. You can't say that, okay, in total 1 gallon of water comes to point B, and then in total 0.5 gallon leaves. It's not going to happen. So if 1 gallon comes in the pipe AB, from pipe BC and pipe BD, you have 1 gallon leaving in total if you add it together. As the very basic for the circuit. If you have a node, and what we call the node, if you have a node, is just if you have a point that assume a couple of wires connect to that node. So if I have a node here, okay, that's a node. And any node is the junction of wire. This, in a simple word, node is junction of wire. So similar to what I have here, if I says that, for example, here, I have the I1 enter the node. Let's name them. So it's A, B, C, and D. If I1 enter the node B, then similar to that, I expect the same amount of current in total leave. So if I1 comes, then I2 and I3 leaves. What I expect is I1, whatever enters, should be equal to whatever leave, should be equal to I2 plus I3. In other words, if I rewrite that, I would say that I1 minus whatever enter minus whatever leaves should be 0. So if I subtract whatever enter minus whatever leaves, it should be 0. And usually it is up to you, but usually I myself will look at that. I mostly consider the one enter as positive and the one leaves as negative. You can do it the other way, it doesn't matter, as long as you keep the sign constant. In general, if I want to write what the Kirchhoff law says, the current law says, is that this is what it says. It says sigma I for every node. Let me put it like that. For every node, you can say that sigma I, that enter or leave to that node is going to be 0. This is what the Kirchhoff current law says. So every node in your circuit you choose, every node, it doesn't matter. Every node you choose, if you add all the current get in and and subtract it from all the current leaves, it should come 0. So that's the very first law that we use it a lot during our analyzing the system. So this is the base of that. Sometimes you might, I would give some examples. Sometimes, for example, if I have something like that, an element like that, and then there's a node, and then there's an element like that connected to that, and then it's going there. So if I have something like that, if I go ahead and says it's the I1 coming here, and then I have this node here, and let's call it a node A. So if I1 goes through this wire and through this element and enter the node A, exactly the I1 should leave that node A. So if this I1 goes to A, because there's only one way out, all the I1 should leave. So I would say that if this I1 in that horizontal wire or element here, I'm going to exactly have the same I1 here as well, because whatever enter the node A should leave that node as well. As I said, sometimes, for example, in our analysis, we might not know the direction of that I. Sometimes we just assume the direction of the I. Again, assume we have 3 like that as a node A. And then assume we don't know what's happening here, so we just assume all the direction. So I assume, let's assume the direction I consider is like that. Let's assume all the 3 I like that. Later on, you will see when we start to analyze the circuit, because we don't know the direction of the I, we just assume some direction. And sometimes it may happen like this, that all the I you consider is gonna enter A. It doesn't matter, even if it happened like that, you just write it the same way. So you are going to say I1 plus I2 plus I3 should be 0. So when you do the analysis, one of them would be, or two of them would be comes out negative. So don't need to be worried about them. Just remember, when you put the, for example, you consider all of them integer, just add them all. If you consider all of them leaving, the same thing. Don't get confused. So again, if I have the same thing here, and then I have, assume all of them leaving. So assume I have I1, I2, and I3. So all of them is leaving. Again, I would do the very same thing. I would say that negative I1, negative I2, negative I3 is 0. And then when you analyze the circuit, some of them may come positive, some of them will come negative. And you will know if the value you calculate for the I comes negative here, the value you calculate for the I comes negative here, you know that the direction you assume is wrong, is going in the opposite direction of what you assume. However, when you write the KCL, don't worry about anything. Just look at the, add all the current get in, and then subtract all the current leaves. And then when you put it together, it should be 0. That's the first law that we will use it, and we'll use it a lot in the rest of the course. So it's the very first law that we have. Okay. So the next one, the next law is the Kirchhoff Voltage Law. So, or usually they call it KVL. Remember when we talk about the Kirchhoff current law, we said that everything entered a node. We were talking about the node, and the node is the junction that the wire gets in. Here we are going to talk about the loop, and the loop is any closed circuit that you can have in your system would be considered as a loop. So, for example, here, before I go ahead and say, now, I wouldn't put any element, I just put the wire, just for the sake of that. So if I have, well, let's put some element as well. If I have something like that, no, what is it like this? And then I have, for example, another element here. And then I call the nodes. So these are wherever we have, use another color. Anywhere we have the junction of wire, there are the nodes. So these are the nodes that we have. Anywhere we have the junction of the wire. So these are our nodes. I'm gonna just call them, for example, A, B, C, D, E, and F. Now, for the loop, when we are talking about the loop, it means that any closed circuit that I can have would be considered as a loop. So for example, here, I can have the loop 1 would be the loop that goes from A, B, C, and D. So if I want to say the loop 1 is the loop 1 that I start from the A, go to B, go to, oops, sorry. A, B, E, and F. So the very first loop is that I start from the A, go to B, go to E, and go to F. So that's, I will call it, for example, the loop 1, and I say I will rotate like that. So A, B, E, and F. So that's the loop 1. The second loop I can use is B, C, D, and E. I can say that B, C, D, and E. So I can go ahead and set my second loop again. It's a closed loop. So I can start from the B, go to the C, go to the D, go to the E, go back to B. That's my second loop. And here I can have the third loop, which is going to be A, B, C, D, E, and F. It means that I can start from the point A, go all the way back to the point A. So if it's a point and it's a 3. And so again, I go from A, B, C, D, E, F, and back to point A. So any closed circuit that you can have, any closed wires, connection of wires and elements you can have, it will consider a loop. And you can rotate also the other way. So here I rotate clockwise, you can rotate counterclockwise. For example, instead of going from A to F, you can go this way. For example, go A, then F, then E, then D, C, B, D. You can rotate the other way around. It doesn't matter. Either way, that's okay. Remember that. So that rotation I, again, draw here is just my convention. I use it that way. You can rotate the other way. You can rotate the counterclockwise. It doesn't matter as long as you have the closed loop. So as long as you have the closed loop, it's going to be okay, regardless of which direction you're rotating. Now, what the Kirchhoff law says, the voltage law says, is that in every loop, no matter which loop or how you rotate in that loop, in every loop, if you add all the voltage together, it's going to come at 0. So if I add all the voltage in the loop A, B, E, F together, it's going to be 0. The same if I do for that, the second loop is going to be 0. The same for the loop 3. So it says that if I choose a loop, regardless of which loop I choose, if I add all the voltage in that loop together, it's going to be 0. Now the point is that, remember when we talked about the KCL, I said the current law, I said I would consider everyone goes in as a positive, everyone leaves the node as a negative. So here also we have to choose some convention about what voltage is positive, what voltage is negative. The easiest way of doing that is that when you're rotating, if you hit positive polarities first, assume it is positive. If you hit negative polarities first, assume it is negative. And I will give you an example here to show you how it works. So for example, assume I have 3 elements, a loop, a circuit with a single loop. Like that. And then assume the polarities in this circuit is like, so I will call this, for example, assume it's the A, this is the B, this is the C, and it's going to be negative, positive. Assume it is like that. It's positive, negative. When we do analyze the circuit, then we know about them. But for now, you assume these are the polarities we have. Now I have one loop here, and I want to write the KVL for this loop. If I have to, first I have to choose the direction of rotation. So I would say I would rotate like that in this loop. So it's my first loop, it's only one loop. I will rotate from that, and I will start from this point. It doesn't matter where you start, as long as you go back all the way to the start point, it's okay. You can start from any other node, but you choose a node, start from that node, and make sure you go all the way back to that node. So if I write the KVL in loop 1 here, so I start from this point here. I start from this point here. I will go up. I hit the negative polarities. You see, I hit the negative polarities. Because I hit the negative, I will assume it as a negative. And then the voltage that this element has. So this, assume this element has a VA, the voltage in this element is VA, the voltage in this one is VB, and the voltage in this one is VC. So I hit the negative, so I put the negative sign, and then the magnitude of the voltage in that element. So it's going to be VA. I move, so disregard the next, in every element, you only work with the first polarity. So disregard the second polarity in the element. I move to the next one. The first polarity I hit is positive. So I'm going to put the positive sign and then the VB. Then disregard the second polarity, move on. I come here, again, I hit the positive first. So again, I put the positive, and then I write the magnitude. And then I go all the way back to where I start. There's no other element there. There's no other voltage there. So it's gonna be 0. And remember, I will talk about that also later. The wire does not have any voltage. The voltage in the wire is always 0. So no wire has any voltage in it. So it's going to be like that. So I start from that corner point, corner node here. And then if I hit first negative, I put the negative sign. If I hit positive, I put the positive sign. And then I add all the voltage together. And then that's how I'm going to have the KVL. And then we will write it for every nodes we have, every loop we have in this system. And in general, I will work through that later on, but in general, it works like that. When we have a circuit and we want to analyze it, we write the KCL and KVL for all the nodes and all the loops, and then we solve them together, and then we can get the, along with the Ohm law, we can get the voltage and the current in the system. And again, when we are talking about analyzing a circuit, this is all we talk about. Find the current and voltage in the elements or the wires. That's all we want to find. How much current we have in each element of circuit, how much voltage each element of circuit has in it. So this is the second law that we will use it. And again, as I said here, you can write it for any number of loops, any closed loop you can have, as long as you start from one node, rotate all the way, goes back to that node. So it's the second law that we will use as the Kirchhoff Voltage Law, or KVL. The next, before I go to start to talk about the next law, there are two concepts that you, and we will work again with them a lot, and it might seem a little bit confusing at the beginning, but don't worry about them. When we keep working with them, you will get that. The concept that is that if we have the elements, not all the elements, but most of the time our elements are either sitting in the series or parallel format respect to each other. And if they are in series or if they are in parallel, they have some specific characteristics that we can use it to solve the circuit more easily. So first, before I go ahead and say what are the series or parallel elements. So what about series circuit? If when we will talk about the series, it means that elements come one after each other. It means that end of one element directly connect to the end of the next element into the circuit we have. So if I comes here and says that, for example, this is the element A, and then there is the element B, A, and then B. Look at that. A directly connected to the B, and we call this as a series. So there's nothing between them. One of them directly connect to the next one, and nothing except a single wire is between them. When we have this series, it's a very important point in the series is that if we have the I here, then we have the I here, then we have the I here. If the elements are in series, they all have the same current. So if we know the current in one of them, it's like that we know the current in all of them. So if you have, that's very important. So probably the most important point about the elements being series is that because when I go through that one, the same I have to leave again, and then the I go through B, the same I have to leave. So all of them share the same I. And when we are analyzing the system, we only need to calculate, for example, want to calculate the I need only calculate the I for A or B. Because if I calculate for A, the I for B is exactly the same. I don't need to recalculate that or calculate it again for that. But remember that they should be directly connected to one after another one. So, for example, if I have A, and then I have B, and then I have C here, it's going to be A, it's going to be, and then I have a note here that just the wire there, and then I have the C. A and B are series, but B and C are not in series anymore because there is one wire between, there are two wires between them. It's not a single wire connected end. There is something in between, in addition of that single wire. Because that is in there, B and C are not considered series anymore. And you know that if there's a, you can see that if there's a I going here, the same I is going here, but that I would be split here between, becomes I1 and becomes I2. So as you can see, the C is not in series, although it might look the C is in series in B with A and B, it's not, because there's something in between them. One thing before I move ahead for the nodes, remember that if there's a single wire, you can always move the nodes. For example, if I have something like that, and then I have a node here, and then I have this here, and then I have this here, and then I have this here, and assume it's a point A, B, C, D, and then I have these two nodes E and F. look at these two nodes. These two nodes are only connected with the wire. So you can just simply, when you do the analysis, you can just remove that wire and put the E and F on top of each other. So remember that if there's only a wire between them, you can remove it or you can add it. It doesn't matter because wire does not do anything. So by adding it or removing it, is not going to happen anything. So this one is equal to, if I go ahead and say there's a and then goes there, there's a so if this is a, this is a B, this is a C, and this is a D, and then here are E and F. I just put E and F on top of each other. I remove the EF wire, I put them on top of each other. These two are the same because that wire doesn't do anything. Or sometimes you may go from this to this one. You may want to separate the nodes. But remember that separating the nodes or putting on top of each other doesn't change anything as long as it's a single wire. That single wire doesn't do anything. So these two are the same. So don't get confused. E and F are not two separate nodes. They behave exactly the same. So you can just put it on top of each other. Assume there's one. You don't have two nodes E and F in case of behavior. Although physically we have it, but behavior-wise, it likes that E and F are a single one. They are not two. Let's look at another example for the series example. For example, if we let's see. If I have a circuit like that, and then I have, so it's A, B, so it's C, D, and E. If I had a circuit like that, and I want to look at them, in this circuit, I would say that, look at here, A and E are connected directly on one end together. Forget about the other end. As long as one end is directly connected together, they are series. And why? Because if I have a, for example, I1 here, just assume, if I have a I1 here, go through E, that exact I1 has to go through A. Look at that. So these are in series because whatever I go through E, assume it's going this way, I have to go to A as well, or the other, if the I1 is the other way around. If the I1 goes downward here, if whatever goes through A, it has no choice that all of these goes through E. But these two are in series. But if you look at A and B or B and E, I come here, but between them, there's the third wire here. They are not, although those ends are connected together, but since there is more than single wire, these two are not series anymore. So A and E are in series, but B is not in series with E or either E or A. The same here, if I look at C and D, one end of them are directly connected to each other. There's nothing between them, it's just single wire. Although it's broken, it seems to two wire, but it's just single wire. So everything, for example, assume if this is an I2 go like this, all these I2 have to go through this single wire and go through the D. So these two are in series, but B and C are not in series. Why? Because if I go from B to C, there's this wire here. So this third wire here is mess up everything. They cannot be the same here. If I go from D to B, there's this third wire here. It messed up everything. So B is not in series with any of the other elements because it's not connected directly to any of the other elements. A and E are connected directly, just with one single wire, so they are in series. C and D are connected with the single wire directly, so they are in series. But B is not in series with any of them because it's more than single wire between B and any other element that you look into the system. So we have two series here, A and E and C and D. And then we have the B by itself sitting there. So this is what we will consider it as a series. The circuit is in series. So remember, just one element goes right after the another, but just with a single wire, nothing else. Even if there is a third wire there, or the second wire, as we said, if there's going to be a node and the additional wire, then it's not going to be in series. The only way that are in series that the end of one of them correct directly without anything else with a single wire to the next one. So this is the one. So this, again, the one reason that is important for us, because we know that, for example, in this one, when we do analysis, we know that if I calculate I1, if I know the I in, for example, the E, there's exactly I in the A. So I don't need to, again, recalculate it. The same here. If I calculate the I in C, I don't need to calculate I in D because they are in series and they have the same current. So that's why we use the series in the circuit. So it helps us to find some of the elements without doing calculation. Or at least sometimes it eliminates the unknown in our calculation. Then the next one are the parallel circuits. The elements are parallel in the circuit. So remember in the series when it says that the elements are in a series if one element, end of one element follows by the end of the another, directly one end connected to another one. When it comes to the parallel, it would say that each corresponding end of element should be connected to each other. So if one end of the elements connected to each other and the other ends also connected to each other, we would consider them as a parallel. So for example here, if I want to draw that, so if I have element A and then I have element B. So if the first end of them are connected to each other and the second end of them also connected to each other, we will say that A and B are parallel. So remember, in this case, both ends should be involved. In the series, we would say that if one end of one of them connected to another end of the other one, that's series. But here, both ends should be connected. So both ends should be connected to each other, like here. So one side connected to each other, the other side also connected to each other. This is how we will say that the two elements are in parallel. In the series, that when we have the series, it says that whatever current goes from one of them, it goes exactly to other one. So because of the first or the current, the Kirchhoff law, when you say Kirchhoff current law, the same. If I write the Kirchhoff voltage law for this node, because I have only A and B. This is a loop here, sorry. There's a loop here, and I have only two elements in this loop. If I write the Kirchhoff voltage law for this one, it means that the voltage of A plus the voltage of B should be 0 if I add them together. In other words, when you go there and you work out that, the point is that the voltage of A should be equal to the voltage of B. So in the series, the current in the elements are the same. When they are parallel, the voltage in the elements are gonna be the same. And usually when they are in parallel, for example, they would show them like that. So assume, like look at another example. Assume I have 1, 2, and 3 elements here. No, let's do something here. Now, you see that I'm gonna just rotate that. So draw it. I will rotate that and draw it. So this is more like what you see in the circuit. In the circuit, if I want to draw this, usually they draw it like that. So it's going to be A, and then it's going to be B. So it's going to be A, it's going to be B, and then both ends of them are connected together like that. So usually there are, so if it's a C here and it's a D here, it's going to be C here and it's going to be D here. Usually they draw it like that in the circuit. So it's like that. So the C comes split into two, A and B connected, then join back together and goes. It's like that. The C goes split to two, comes back, join together, goes to D. So this is, these two are the same. This is usually easier to understand what's happening. This is how it's drawn in the circuit. So this is what you see in the book or any circuit you look at. That. Again, if you look at that, it means that these two are parallel because here one end of them are connected to each other. Here another end connected to each other. And if the voltage here at the very beginning, for example, here the VA is equal to VB. Whatever voltage that element A has is going to have the same voltage that we have in the element B. Another form that it might be just another example. I said if I say, assume I have 3 elements in parallel. So I have 1, 2, and 3 elements in parallel. So we'll say that is element A, B, is the C. So, and to be in parallel, again, one end of all of them should be connected to each other. And another end should be connected to each other as well. So if I assume I call here E and here F. So I have 3 elements here again. Look at that. The first end, the one end of the left end, all of the left end connected to each other, all of the right end connected to each other. So these are going to be in parallel because their end, the corresponding end, all connected to each other. How do you show it in the book? This is how you're going to see that in the book. So it's going to be look like this: A, B, and C. And then you have the wire, connect them like that. And the wire connect this like that. So again, it's going to be, if this is the A, this is the B, this is going to be the C. And if this is the E here, and this is the F here. So here E comes, then split into 3, connected to A, B, C. then joined back together and goes to F. Here the E goes, split to the 3, goes to A, B, C, they join back and go to the F. So this is how you will see it in the book. And if you have something like that, again, they have the same voltage. So V in A is equal in the V in the B is equal to the V in the C. So these three have the same voltage as well. So another, for example, if I want to look at another example, if I have two elements sitting here, and then I have three elements sitting here. And I said, for example, let's say A, B, C, D, E, and F. So if I look at these elements, I would say that you'll say these two, if you look at the A and B, one end connected to each other, the other end connected to each other. So A and B are in parallel to each other. If you look at it, because the corresponding end is to each other. So I would say that here VA, VA is equal to V at B. If I look at that, this end, okay, this end, the one end of the D, E, and F connected to each other, the other end of D, E, and F also connected to each other. So these three also, these three, D, E, and F are in parallel. So V for D is equal to the V for the E is equal for the V for the F. C, if you look at it, is not in series or parallel with any single of other elements, because if you look at C here, one end connected to A and B, the other end is connected to D and C and E. So it's not directly connected to any element. Is also neither both end of it connected to the same element. So it's neither in series or parallel to any of single elements that we have here. So if you look at that, we have two parallel here, three parallel here, and the C here for itself, which is neither series or nor parallel to any of the other elements we have in the system. Again, similar to that, this is the most important one. When we have the elements sitting in parallel, the important point is that they have the same voltage. So if I calculate the voltage in, for example, F, I know the voltage in D and E, so I don't need to recalculate them. And the same here, if I calculate voltage either of A or B, the voltage in the next one is also the same. So I do not need to recalculate the voltage in the other one. And we use this in the next chapter when we start to analyze the system. We use the series and the parallel elements to simplify our circuit. So when we started, we look at the circuit and say if there's anything series, we probably look, one of the very first thing we look in the circuit is that, can I find anything in series or a parallel? So it helps me to simplify my circuit. It helps to eliminate the number of unknown, so I can solve the circuit with the less equation with less amount of work. So is there any question about what we have up to here? Now let's look at an example, see how we can use what we learned to work out. Assume we have a circuit, let me see, yeah. Assume I have a circuit like that. A so yeah, assume I have a circuit like that. This is going to be A, B, C, D, it's going to be F, and it's going to be E, and then it's going to be the polarities like that, positive, negative, positive, negative, positive, negative, negative, positive, negative, positive, and positive, negative. And so I have a circle like that, and I know, for example, the V at A, that in here the VA is 10 volt, V at C is 15 volt, and V at E is 20 volts. So we have these three, and then we want to find the voltage in other element of these circuits. So we have the voltage in three of them, in A, in E, and in C, and we want to find the voltage in the other three elements in the circuit. So yeah, we have a circuit like that, and want to find voltage like that. Before I move and solve it, probably just to look at it, you can say that A and E are in series. You can see it's directly connected to each other. And D and F are parallel. So one end of them connected to each other, the other end also connected to each other. So D and F are parallel, A and E are series. And the other two, the B and C, are neither parallel nor series. They don't have any other criteria of being series or parallel. So I want to find the voltage, so I would start with the Kirchhoff voltage law, and I would say that the loop one, I would consider this one as a loop one, this one. These loops, the very left loop, I consider as a loop one. I would say that I would write the KVL, Kirchhoff voltage law, in loop one, would say that sigma V is going to be 0. So if I'm in the loop one and I add all the voltage together, it should be 0. So where I'm going to start, I choose one node and I start again. I choose this node here at the very lower corner here. This is the node I start to rotate. I will rotate through my loops and go back to that node. So if I start from this corner here, I move up, and this is my rotation. I go clockwise. If I go here, the very first sign I hit is positive. So I would put positive and then the VA. Then I keep going in that loop until I hit the positive. So I put plus, and then is the VB, the voltage in the second element. Let's put it like that. So it's so VA, VB. And then if I keep moving, I go to the next element, I hit the negative sign here. So I put the negative sign and then the VE, the magnitude of VE. And then I will reach wherever I was at the very beginning. So I finish the loop. So I start from this left corner, rotate it and go back. So this should be 0. So if I substitute the value, the VA is 10 volts. Then plus the VB, which I don't know how much is this, then minus VE is, which is the minus, and the magnitude of VE is 20 volt, is 0. So if I do solve that, then the VB would be comes out as 10 volts. Now, if I do that, so that's how we calculate the VB. So now we know that this VB is 10. Now I have these three. Also I have VC and I want to find the V at D and F. So to find the D, I can choose either of them. If I want to find the D, I can go through this middle loop here. I choose the loop that has the D in it, so I choose this middle loop. To find the voltage in F, I can go and choose the loop that F is included. So it can be this loop here, or it can be the very outer loop. And I will show you later how it works. So first I will go ahead and set, because it's easier, I will go and set, I will find the voltage in D. To find the voltage for D, I will go in the second loop. So it is the loop 2. I write the KVL in the second loop. So if I write the KVL in loop 2, then the sigma V should be 0. And so for the loop 2, again, I will start from this corner here, go all the way through the B, go through the C, go through the D, and comes back to that point. So it's the second loop I choose. So I start from this point, I go up, I hit the negative sign here, the negative polarity. So I would put the negative and then the VB. And then I will go ahead, go to the C, I hit the negative sign again first. So I put the negative and then I put the VC. I go again to the D, I hit the negative sign again first. So I put the negative and then we'll put the VD. And then I go back to where I started. So it's going to be 0. And now I substitute the magnitude of the VB. Don't get confused. If the VB or VC or VD, the magnitude was negative, just put the negative. So it's going to be negative times negative is going to be positive. So this negative sign I use in front, or the positive sign I use, is regardless of the magnitude. The magnitude itself can be either negative or positive. That's another thing. So don't get confused. What you have, what anyway. So here that we have everything positive. So what we have here, I started from the B, it's got the negative and the magnitude is 10. Then I have for the C is the negative and the magnitude is 15. And then I have negative and VD is 0. And then if we do the calculation, the V sub T, this comes out as 20, negative 25 or 24. Yeah, it's a negative. So, the very last thing today I'm going to very briefly talk about them is the elements in the circuit. So a couple of elements in the circuit, and before I Richter Ohm law, and then I will continue from there. The circuit elements. A couple of elements that we will talk about them in the circuit, and I'd say one of them is the conductor, or simply or just wire. I'll say that. Then the sources. So the one of them is that. Then we have the sources, which might be a voltage source, or it might be current source. And then we have the resistor. So these are the basic elements that I will talk about them for now, and then later on we'll talk about the other elements that we can have it in the system, in the circuit. The very first, or the basic one that we work for, is just the conductor or just the wire. The ideal wire that we have is that, remember I talked about the wire. Wire connect the elements together. So if I would say that you will talk about the wire, assume I have something like that. I have an element here. And then, so these are the wires that connect our elements together. So these what we call it the wire. So any wire that connect them the elements together. In general, when we talk about the wire, is that the wire does not have any voltage. So the voltage in the wire is 0. And what we have, now there are two types of the wire that we will use. Look at this circuit. Assume that's what we have here. If I have the I going through that top part of that, and I have an element here, and then I have a wire here. All the, I will work on that later, but just look at that. All the current, this current goes through this wire. So all that is going to be like that. So it's going to be I, and here is going to be 0. So I here is going to be 0. So if I have a wire, because in the ideal wire, I don't have any resistance, all the current goes through that, and nothing goes through this element here. And this is what we have here that you can see. That if we have something like that, this one is called short circuit. So it's a short circuit. So here the same here, because there's a resistance in this element, all the current go through that wire. Nothing goes through that element here. Everything goes through that wire. That's so it's like that this element is not there. It doesn't do anything in our system at this condition that we have. So this is one of the ways that we know that because ideal wire doesn't have any voltage in it. So this is the short circuit in that. If the other cases that we about the wire that we need to know is that, again, consider that the very same thing like that. But this time, assume we have the wire that is not connected. It just comes to this point, but they are not connected. And then we have the same I going here. This time it's going to be the opposite way. So all the I goes here and nothing goes here. I is 0. The I goes to this end. When this happens, in this case, when this happens, so here the V is 0. Here, if let's say, so if here we have the A, and here have the A, and then we have the VA here. Here we have the VA. If this is the VA here, the same VA is here. So here V is 0, here V is equal to that. So also if this is a positive negative, it's going to be positive negative. And this is called the open circuit. So the difference between these two is that here, if the wire is connected all the way through, all the current goes through, and there is no voltage here. Here, no current goes through, but there is a voltage there, and the voltage is exactly the same as the voltage that you have in that element here. We have it. By the way, because here we don't have any current go through this element, its voltage is going to also be 0. But here, the voltage goes through that. So there's a voltage. So let me clean that so you don't get confused. There's no voltage there. So here, in other words, if I have a connect around the element, if I have a wire along the element, all the current goes through that element. If I have a wire along the element, but I cut it through, no current goes through that, but it's going to have the same voltage as that element. These are two cases. Just remember that, or memorize them, or remember that, because then later on when we go on, we use these two conditions for analyzing the circuit. So when we remember, when we talk about the short circuit, means that there's a wire around that element. And when we talk about the open circuit, means that we cut the wire. There's no current going there. When there's a short circuit, all the current goes through that short circuit, no voltage. When there's an open circuit, no current goes through, but we have the voltage in that wire. So again, remember, if you have the wire, if you have the connected wire, the voltage is always 0. If you have the cut wire, if you have the open wire, the voltage is equal to the whatever element those wires are connected to. I'm going to stop here. The next time I'll start to talk about the sources and the resistors.